Next, we have a very cool example. We have a piece of moon rock that was initially entirely made out of potassium. So it was initially 100% potassium. So in other words, 100% K. And right now, our sample of moon rock contains an equal number of potassium and argon atoms. So it's equal in number potassium and argon. And our task is to determine how old this piece of moon rock is. Now we have some additional information that we can use. So the half-life of potassium is 1.28 billion years. So 1.28 times 10 to the 9th years, or 1.28 gigayears, if you will. And we have some additional information about potassium and argon. When potassium decays, 1 out of 9 times the decay results in an argon atom. In other words, 1 out of every 9 potassium atoms, so 1 out of every 9 potassium atoms that decays into argon. Okay. And using this information, we have to figure out how old the moon rock is. So it was initially 100% potassium, so these are the big bullet points. So initially all potassium. Now there are equal amounts of potassium and argon. The half-life of potassium is 1.28 gigayears, and 1 out of every 9 potassium atoms decays into argon. Okay, so how do we go about this? This is a fairly complicated problem. So let's just start with what we know we can do. So we can start with just looking at the potassium. So we can, since we know the half-life of the potassium, we can model how much potassium is left as a function of time. So let's do that first. So let's just look at the potassium part. So let's say part 1, potassium. Okay, so let's say that we'll introduce a new parameter. So let's say N is the number of potassium atoms initially present. Or maybe the number of moles of potassium atoms. But since I'm not actually going to solve for N, since I don't know the initial amount anyway, it doesn't matter if it's the actual number or the number of moles. If I actually knew the number of atoms, it would probably be easier to represent it as moles because, there are usually a lot of atoms in a small amount of something. So instead of having astronomically large numbers, probably better to use moles instead of atoms, but since we're not using the actual numbers, atoms will work just fine. So N is the number of potassium atoms that were originally present in this piece of moon rock. So say K of T is the number of potassium atoms present after T years. So instead of using years, we have this half-life. So after something, our half-life was 1.28 times 10 to the 9th years. So let's scale the variable for time and say present after T half-lives of potassium. So in other words, T equals 1 represents 1.28 gigayears, or 1.28 billion years. T equals 2 represents 2.56 billion years, and so forth. So I'm going to do myself a little bit of favor and actually measure T in the number of half-lives. It's basically just this, why set it to be a year when we have this natural amount of time available to ourselves? So K of T is going to equal the initial number present times 1/2 to the t. See how that works? Since t is the number of half-lives, when t is equal to 1, it's going to be 1/2 of the initial number of atoms. When t is equal to 2, it will be 1/2 squared, or 1/4 of the initial number of atoms. When t is equal to 3, it will be 1/8 of the initial number of atoms, and so forth. So this is the number of potassium atoms as a function of time measured in half-lives. If I didn't do that, I don't have to do that. If I say t in years, then what would that look like? So let's look green for an alternate reality, alternate universe. K of t would equal n 1/2 to the t divided by 1.28 times 10 to the 9th. So we would have to have t over 1.28 billion, and this t is in years. So if you want to use t in years, this is what your function would look like. It would look like n times 1/2 to the t over 1.28 billion. So to save myself a little bit of headache, I'm doing it without the over 1.28 billion, and just saying, okay, t is just the number of half-lives. So when t is equal to 1, that's 1.28 billion years. Now I wrote that down after t half-lives of k, so that's the units for t. And that's so that I remember what t is. So in the end, when I get an answer, like say 2.5, I have to remember that's not 2.5 years ago, that's 2.5 half-lives ago. So that's k. Okay, so k of t is equal to n 1/2 to the t. So this is the number of potassium atoms remaining after t half-lives. Okay, so that tells me how much potassium is left over. So this is the number of potassium atoms left after t half-lives. Now we have to factor in the argon part. So we know that 1 out of every 9 decays results in argon, and then presumably argon doesn't decay. That's the end of the chain. So 1 out of every 9 potassium decays results in argon. So to figure out the amount of argon, so that's my next step. I want to get I want some function or some representation for how much argon is present at time t. So to do this, well, I probably need to figure out the number of the amount of potassium that has decayed, right? So how many potassium atoms have decayed by time t? So this is the amount of potassium present, so how much has decayed? Well, so let d of t represent the number of potassium atoms that have decayed during the first t half-lives. Okay, so d of t is how much, the number of atoms that have decayed. So how would we figure that out? Well, d of t, well, it should just be the initial quantity present, initial amount, minus k of t, how much is left, the amount that remains, right? Makes sense. You start off with 100 grams, you have 30 grams left over. How much is decayed? 70 grams. So that part's not rocket science. So that's a formula that relates k of t to d of t. So in other words, the amount that decayed is going to be n minus k of t, which is n times 1/2 to the t. Now I'm going to factor out the common n and just write d of t is equal to n times 1 minus 1/2 to the t. So this is the amount decayed. Now we know that, so this is literally the number of potassium atoms that have decayed. Now 1 out of every 9 of those turns into argon. So 1 out of 9 gives me argon. So now I know how much argon I have, right? So the amount of argon, so let's say A of t, oh, hello, a little surprise. So let A of t represent the number of argon atoms at time t in half-lives of potassium. Okay, well, A of t should just equal the number of potassium atoms that have decayed over 9. So in other words, A of t is n over 9 times 1 minus 1/2 to the t. And that is how much argon will be present at time t. This t has to be inside this outer parentheses right here. Okay, so let's do a quick reality check and make sure this makes sense. Now initially, the rock is supposed to be 100% potassium. So the amount of argon in the rock at time 0 should be 100%, should be nothing, right? Because the rock's all potassium. So let's just look at what A of 0 is. Well, A of 0 is n over 9 times 1 minus 1/2 to the 0. Now 1/2 to the 0 is just 1. So we have 1 minus 1, which is equal to 0. So that works out. So that leads me to believe that I'm on the right. Well, at least that is consistent with what I would expect. It's very useful to do quick reality checks because sometimes you might make a mistake, and if you do a quick check like that, you might catch it. Okay, so basically what we have so far, summary so far. So far we haven't used any logarithms, but that's okay. So we know K of t was n times 1/2 to the t. And then A of t, the amount of argon, was n over 9 times 1 minus 1/2 to the t. So we have these, throw in some red, we've got these great formulas for the amount of potassium and argon at the present time. We don't know what time it is, right? We don't know how old the moon rock is, so what are we actually trying to solve for? We're trying to solve for t, right? Because what we do know, we know something about the present. So we know something about the present. Right? If we didn't know anything about the present, we probably wouldn't be able to solve for t. And what we know is that the amount of potassium presently is equal to the amount of argon. And using that, we have to figure out how old the rock is. So what we do is we basically have to set this number of potassium atoms remaining after t half-lives equal to this, the number of argon atoms present after t half-lives. So we set that equal to this. So let's set those two things equal. So we have n times 1/2 to the t, that's the number of potassium atoms, it's equal to n over 9 times 1 minus 1/2 to the t, like that. And now we want to solve for t. So first let's divide by n. So we'll cancel like that. Let's move this 9 up here. So we get 9 times 1/2 to the t. It's equal to 1 minus 0.5 to the t. So next, I'm going to add this to the other side of the equation. And so I get, and I'm going to also swap, I'm going to put the left side on the right side and vice versa, just because the 1 is equal to, okay, this gets moved over here, so 9 times something plus that something is just going to be 10 times 0.5 to the t, which means 0.1 is equal to 0.5 to the t. Looking simple, ln of 0.1 is therefore equal to the ln of 0.5 to the t. So we now use our log rule. When we have ln of something to the something, the exponent can be pulled out front. So we have ln of 0.1 is equal to t times the ln of 0.5. So therefore, I'm going to switch the two sides again. T is equal to the ln of 0.1 divided by the ln of 0.5. Sounds simple. Let's see what we get. Ln of 0.1 divided by the ln of 0.5 is approximately 3.321928. So that's the number of half-lives that the age of the moon rock is. Now, the half-life was 1.28 billion years, so let's multiply that by 1.28. So the moon rock is approximately 4.252 billion years old. And that's the final answer. 4.220, about 4.25 billion years old. So it's a pretty cool problem.